Hexagonal space lattice. The primitive translation vectors of the hexagonal space lattice may be taken as a1 vector equals a square root 3 over 2 x hat plus a over 2 y hat. A2 vector equals to minus a square root 3 over 2 x hat plus a over 2 y hat, and a3 vector equals to c z hat. A, show that the volume of the primitive cell is a square c square root 3 over 2. B, show that the primitive translations of the reciprocal lattice are b1 vector 2 pi over a square root 3 x hat plus 2 pi over a y hat. b2 vector equals minus 2 pi over a square root 3 x hat plus 2 pi over a y hat. And b3 vector equals to 2 pi over c z hat. So that the lattice is its own reciprocal but with a rotation of axes. Part C, describe and sketch the first Brillouin zone of the hexagonal space lattice. Now you will remember that we have actually solved part A and part B of this problem in the video reciprocal lattice of a hexagonal space lattice. So I refer to this video for the solution to parts A and B. As for part C, we have to describe and sketch the first Brillouin zone. First, we have to concentrate on one of the top or bottom base of this simple hexagonal space lattice. So here we have a hexagonal lattice in 2 dimensions, and we can connect the lattice point in the middle to the nearest neighbors, and to form the Wigner-Seitz primitive cell in the reciprocal space. That's going to give us the first Brillouin zone. So what we do is we connect it to the first neighbors. So first we have a neighbor that is connected to the center lattice point by the vector b1, and then we have one that is connected by b2. We have another one that is connected by minus b2, and this one that is connected by minus b1. And this lattice point is basically connected to the center point by a vector b2 minus b1, and this one is connected by basically b1 minus b2. So we find the perpendicular bisectors at the midpoints of b1 minus b1, b2 minus b2, b1 minus b2, and b2 minus b1. So we see that when we connect the perpendicular bisectors, the smallest area that is contained within this structure is a hexagon. So we find that we have a hexagonal structure here. Now the first Brillouin zone is going to be the simple hexagonal lattice formed by this described hexagon and the perpendicular bisector of b3 vector and minus b3 vector at its midpoint. So you can see that this red shaded region will be the first Brillouin zone. So this is our reciprocal lattice, which has sides 2 pi over a in the hexagon, and we have in the c-axis 2 pi over c dimension. So you can see that this first Brillouin zone will be this red shaded region. Now, one thing I want to note here is that this is the Wigner-Seitz primitive cell in reciprocal lattice, and you can see that this first Brillouin zone contains only one lattice point, that is the lattice point of the center point that I have used in this description. Okay, so to summarize, our task is to find the Wigner-Seitz primitive cell in reciprocal lattice that is the first Brillouin zone. So this is by definition first Brillouin zone. And in order to do that, we take one lattice point connected to its neighbors, and on the same plane we have these 6 lattice points that is surrounding it. There is also b1 plus b2 and b1 minus minus b1 minus b2, but that is going to be giving us a perpendicular bisector at the midpoint that will not be intersecting the rest, so we don't have to worry about that. So we have to worry about B1 minus B1, B2 minus B2, B1 minus B2, and B2 minus B1 vectors. We see that the perpendicular bisectors at the midpoint form a hexagon, and by looking at the connection on the c-axis, which is or B3 axis, the perpendicular bisectors at the midpoint B3 over 2 will give us plus B3 over 2 and minus B3 over 2, this red shaded region, which will be another simple hexagonal lattice that is rotated with respect to the reciprocal lattice by an angle, probably 30 degrees, as you can see here. And this is going to be the first Brillouin zone.